Well, then now's the time. So the other day when we were talking about different people's labs, one of the errors in one of the labs, they didn't account for the amount of particles they had in there, right? Was that yours, Miss Stells? Was that your? Yeah. So remember they were like taking particles out of the vacuum chamber? And weird, that's going to change things, yes? So the easiest one for my brain to always think about is balloons. If I add particles to a balloon, what happens to the balloon? It gets bigger. Its volume goes up. So if I change the amount, and I use n like number, because it's just a number. If that goes up, then the volume of the balloon goes up. And if I blow the balloon up bigger, it gets bigger. Right? So particles, you can see, are directly related to volume. Follow that? Did we talk about kindergartners yesterday? No. Oh my gosh, it's going to be a long day. Let's talk about kindergartners. If you're wondering how kindergartners relate to gases, I'll help you. In my brain, not yours, in mine, when I am trying to figure out stuff about gases and trying to figure out how they're all interrelated or how they're going to act, or even a lot of times solids and liquids, I always think of the molecules, the particles, as kindergartners. I find kindergartners act a lot like random particles, right? So, like, I'll take something like field day. Do you remember field day when you guys were, like, in elementary school? Yeah, I was thinking we should have field day again. That's a good time. Wouldn't that be sweet? Oh, my gosh. That'd be awesome. So imagine you take kindergartners and you throw them out on the football field, right? You got that? Let's take 50 kindergartners. Sound like a good amount? So if you take those 50 kindergartners and you just like say, go, what's going to happen? So nobody's there, just those kindergartners. You throw them out on the field. What's it going to look like?
Chaos.
It's going to look like chaos. It's like crazy. Which is what gases do, right? Gases just go and they start randomly doing things. And where are those kindergartners going to go? So we're up in the press box watching. What are we going to see?
They'll be everywhere.
Where's everywhere? They would go wherever they want. Can you picture it in your head? They'd be running on the track. They'd be on the football field. Some of them would be over by the flagpole. Some would be in the bleachers. Some would be trying to climb over the fence. Some would be over the fence, like halfway up the cross-country course, right? Can you picture those little kindergartners doing all of that kind of stuff? Yeah. See, I have this because I used to like working at daycare all the time, and that's exactly how it was, right? So they work as a really good representative for gases. And you can imagine if you sent all those 50 kindergartners out there, they would take up so much space. But if I put 1,000, they would take up more space. Duh. Right? Does that kind of click in your brain? And I do that with all the variables. So when I'm trying to think of how it works, I'll say, okay, let's pick another variable. Let's pick pressure. So pressure is force over area, right? And if you thought about it, but you probably haven't, the force we're talking about is those gases running into each other or into the walls, right? So take those kindergartners, picture them in your brain. When you have 50 of them out there, do they ever run into each other? Yeah. Probably. That would be pressure. Every time they hit, you can think of that as one whatever you want, right? What if I took those same 50 kindergartners and I put them in my room? Would they run into each other? Yeah, they probably would a lot more. Why? Yeah, we reduced the volume, right? And we found that in our lab. If I shrink my volume, my pressure is going to go up. Do you see how this kind of really, kindergartners work well for this? We can do the same thing with them out. What if I have those 50 kindergartners in here? Imagine them running into each other, running into the walls, being little kindergartners on crack. And we all of a sudden put 1,000 kindergartners in here. All right, let's go 100. So we put 100. What's going to happen? Are they going to run into each other more or less? they're probably going to run into each other more. They're probably going to hit the walls more, hit the desks more, break way more lab equipment. It's very sad. So if I increase that number, that pressure is also going to increase, right? And like you saw, I could do the same thing with Boyle's law. Little kindergartners, they're so good to think about. So let's change it again. What about temperature? Temperature is actually a measure of what in a sample. What does temperature actually measure?
Kinetic energy.
It's measuring kinetic energy. For most of us, we think about kinetic energy as how things move, right? Like whether they're moving fast or moving slow. So picture 50 kindergartners in here. Picture how they're moving. Can you picture that in your head? Do you see them moving? I don't care how fast they're moving, but I need you to have a picture of how they're moving kind of speed-wise. You got that stuck in your head? All right, add, I don't know, make it 1,000 kindergartners in here. Yeah, that's a lot, in case you're wondering. They'd be like shoulder to shoulder. Crying. Running noses and everything else. How much are they moving when I put 1,000 of them in here?
Very little.
Why?
There's so many of them.
I mean, it'd be really hard, wouldn't it?
Yeah.
Right? Could you see their motion slow down? So what does that mean about temperature? So if temperature is kinetic energy, when you just increased that number, what happened to the temperature? It went down, right? It got smaller. So as that went up, my temperature actually went down. My kinetic energy went down. And that's why I use kindergartners. That's easy for me to think about. Thinking about a helium atom and what that helium atom is doing, that's kind of hard. But imagining kindergartners for me, that's really easy. I don't know what it is for you. So if you have something that works better for you than kindergartners, right? Like puppies. Puppies are cute, right? Oh, good. I was worried for a second. You didn't like puppies. That'd be weird. Puppies are awesome. They're cuddly. Olivia's tired. So pick something that you like that would work, and that just helps make this all make sense. But anyway, that's that fourth variable that we never talked about, right? And once we know this, once we can picture this, we can see who's related to who. Directly related, indirectly related. Do you follow that logic? So let's look at our combined gas law. Where would this go? Where would the n go? Where would that amount go into this formula? With the P and the V? That's the question, right? Where would it go? Nope, it's going on this side. It's going with these guys. So would it go on the top or the bottom? That's our question. Top. So you're saying the things that are next to each other are directly related. But pressure and volume aren't directly related. That's what this says, is this is indirect. Pressure goes up, volume goes down. They're indirectly related. This is directly, right? As one goes up, the other goes up to cancel it out.
Oh, the bottom.
That means it has to go on bottom, right? Because it has to cancel out. It goes opposite of the temperature, which means it needs to be next to temperature. So it would go there. Hey, this is starting to look like a law again, isn't it? But wait, there's more. What do these K's stand for? Yeah, they are. They're constants. But why are they K's? Why aren't they C's or M's or G's? Why are we using the letter K up there for those top three? Boyles, Charles, and David Sachs. What does the K mean? somebody left this chair up there. I think I can move it. Originally, I didn't like it. What, Lauren? I can hear you chit-chatting. What's K?
We're talking about how when it's like a known constant, it gets its own thing.
Yeah.
It's just like,
If it's the same constant every time, it gets its own level, and if it's like a different constant every time, then you just have it be kept.
Do you guys remember that talk? So when we have a constant that changes, like it's specific to that situation, then we just call it a K. So people know that it changes, right? But if it was a real constant, one that never changed, it was speed of light, right? Then it gets its own letter, C. You know, we know gravity on Earth is 9.8 meters per second squared, so we use a G to represent that. Do you follow this logic? K's mean they change. With me so far? And you're probably going, I don't understand why we're rehashing this. You'll get it in a second. Why does this K change with different situations? What could I possibly change that would make this be a new K? So someone's doing a Boyle's Law test. What could I change if I was doing the test that would make me have a new K? Well, my pressure would automatically change my volume, which is what that K is telling me. So what could I change that would mess it up? I could change temperature, because temperature has to remain constant for Boyle's Law, right? If I all of a sudden change temperature, I'd get a new K. Do you follow that? If I look over here for the Gay-Lussac's law, if I changed what, would it mess up my K? Sure, volume would mess it up, right? Because I have other variables that exist. Do you follow this logic? So there's other variables when I'm playing with a gas that happen. Other variables, right? So they get K's because I could change those other variables, then hold them constant, I'd have a new K. This is hidden, so I'll take you through it. There are no other variables. There aren't. And let me give you an example. Pick another variable that you can think of. All right, so think to yourself right now. Give it a second, then we're going to call on David. Think about something else that maybe I could try to change about a gas. You with me? So get in your head something else. Not pressure, not volume, not moles, not temperature. I'm going to change that in my experiment. And that would change this. Okay, David, what'd you think of? Different types? Okay, why would different types of gases matter? That's a good spot. So he goes, yeah, what if I changed it? What if instead of using oxygen, I used nitrogen, or I used methane or carbon dioxide? I'm going to change those. Which, by the way, first thing, didn't we have a group do that? Was that this class? Ooh, first hour in their Boyle's Law experiment, they changed the type of gas. You want to know what was awesome? They thought they had totally screwed up, and I was super happy. Their graph, all the lines were on top of each other. They were perfectly matched. They're like, this doesn't make sense. I used methane this time, and it matches the exact same as the oxygen. And that one matched the same as the CO2. I was like, oh no, weird. Why didn't it matter what type of gas they used? Well, let me ask you this. What are they actually trying to talk about? So they're saying gases, but really they mean something else. What were they thinking would change this? Or maybe you're thinking, no, just the type of gas would. But what would be different about different gases? What's different about CO2 versus argon? Yes, different elements, but what's actually different? What? The mass is different, right? So people are saying, oh, you're changing the mass, right? That would change it, right? If you used gases that were really, really fat or gases that were really skinny. You got to account for that, don't you? Yes, you do. What's temperature a measure of? Kinetic energy. What's the formula for kinetic energy? Anybody from physics here? Some of you are. What's the formula for kinetic energy? One half times mass times speed squared. Oh, wait a second. It's got mass in it. So when we're dealing with temperature, we've got mass. It's in our formula. What other variables did you guys think of? Let's see if we can stump the chump. Right? Can you think of a variable that I don't have in here maybe? One that matters? Joey, what'd you think of? So he said the type of gas, what'd you think of?
Maybe like the location, where it is, I guess. Like, I guess that would be pressure.
Oh, I see what you're saying. Yeah, you're right. That would take in pressure. Yeah. Like if you had different gravity amounts or something weird like that, or yeah. Pressure would take into that account, so you answered that one. What else? Did anybody try to do time? I thought I saw graphs of time. Anybody time things? Nobody timed anything?
Oh yeah.
Oh yeah.
We tried to.
You tried
See
to.
how long it took to go now.
Why wouldn't time work on this? Or why is time included? Where's the time? It's hidden again. Speed is meters per second, right? You've got time included. Your variable's there. In other words, you've got all your variables here, right? So all the ones you can think of, they're included in this formula. That means you can't change anything. Let me rephrase that. I could change my lab here and it would give me a new K, right? Here, I've already accounted for all the variables. In other words, if I changed the pressure here, that would change the volume, which would change the temperature, which would change this. So let's say my K was 5. It's not, but let's say that's what it is. So if I change my temperature, guess what? That would change these. Do you follow that? And this is already accounted for. So it'd still be 5. And if I changed all this, guess what this would still end up being? Because all of the variables are taken into account. Do you follow that logic? Yeah.
Wait, so for each law then is K always the same thing?
K is different depending on the situation for that law.
So, but when you're doing the same like trial multiple times,
Then
is
it's
that
the same.
basically the same
You
thing?
got it.
Even if you're changing little things?
Yeah.
Okay, like we're talking about.
Like if you're like in this one, if the only thing you changed was pressure, your volume will adjust directly or indirectly. Every single. In other words,
Situations, the K will change.
right. So if I did it outside, oh dear, that's going to screw it up. Like it won't screw it up as long as you did all of your trials there. But as soon as you moved it, you just incorporated a new variable and that would change it. But this has all the variables. Do you follow this logic? What does that mean? That means this isn't some ordinary K. It's not a K that changes per situation. It means it's like a real constant. Do you follow that? It's like a real thing. So it's not a K like these. These K's change. This K doesn't. It's actual. It's always the same because all the variables are accounted for. Do you follow that? Let's give it a letter. Let's call it R. Because it's like real. Okay. What number do you think it is? Let's figure it out. It can't be that hard, right? Let's pick numbers for these, right? And see what that'll work out to be. So let's see here. Let's see. I like 1. Do you guys like 1? It makes math really easy, doesn't it? So let's make my pressure. Let's make my pressure 1. And let's use atmospheres because that's what chemists do a lot of times. Let's do number, that amount. Most of the time for amount in chemistry, we use moles. You remember that? Somebody earlier said, why are we using moles? Could we use something else? I'm like, yes. Oh, what else could we use? I'm like, donuts. I'm like when I go to Meijer and I order donuts, that's my amount. Like amount literally means number. In chemistry, that would be dumb to use donuts, because unless you're bringing me donuts, and that'd be sweet. Let's use 1 mole. Does that sound good? Temperature. Let's use 0 degrees Celsius, right? Freezing point of water. That seems pretty common. Oh, another reason why we can't use Celsius. Why? right? You can think of 0 degrees Celsius out there, right? You can imagine freezing point of water. Why can't I use this with my equations? Math people,
Can't divide by 0.
you can't divide by 0. Is that what you're going to say? Yeah, you can't divide by 0. And 0 would be here, 0, 0. That doesn't work. That's like the universe ends or something. So we can't. So I like 0. Probably should change it to Kelvin. Okay. Hey, did you notice what's different between Kelvin and all these other temperature things? Like Fahrenheit and Celsius, there's a big difference. Yeah, there's no degrees. Did you guys catch that? Kelvin is an actual real unit. It's a measure of kinetic energy. So it's like the real deal. Celsius is a degree. They took 0, put it on a line. They put 100 on a line, freezing point of water and boiling point, and then they drew 100 lines. And they said that's 1 degree of a Celsius. And that's how they made it. They did the same thing with Fahrenheit. I think Fahrenheit is based on the freezing point of salt water, right? They said that's going to be our 0. And, then they worked it out. But those were degrees. Kelvin is actually a measurement. And I once had a science teacher who didn't get this. Like they kept saying, oh, you're forgetting the degrees. I'm like, no, there is no degrees. They're like, why wouldn't it be degree? And I'm like, I don't know. Why don't you use degrees centimeters? They're like, it's totally different. I'm like, no, units are units, right? This isn't a degree of a centimeter. It is a centimeter. Do you follow that? Kelvin is an amount of kinetic energy. So it's not a degree of kinetic energy. It is that, right? It's just an average. So anyway, little side note to laugh at people. Oh dear. Now we need something real. We can't make up numbers anymore. Does anybody know what the volume is of a gas at 1 atmosphere? No? Nobody does. Nah, scratch that. Nobody in my classes ever does, so it's not a weird thing. But coincidentally, I do. True story. 1 mole of a gas at 0 degrees Celsius at 1 atmosphere takes up 22.4 liters. I believe that's like part of Avogadro's law, actually. Another one of those fun laws out there. Well, wait, that's all the variables, right? We'll plug them in. What's our R? See what you get. Okay. What are you presenting at?
Business I made.
Yeah, it's a good business.
It's a great business.
Great business. Is your business selling or making?
Restaurant.
Nice. Yes, sir.
Good food. Patriotic food.
Patriotic food. What's a patriotic food? But not French fries?
We have French food.
It's in the name. I think it's like a presentation of how well it's going to do or how poorly. Say that. All right, I'm here chit-chatting, which means we probably figured it out. What did this work out to be? Someone said 0.8.
Yeah.
0.82. 0.5. Oh, it looks like we got 3 sig figs, so let's call it 1.
No.
0.08.
0.0825.
Like that?
Yes. Oh, yeah.
Round, yeah.
You're round.
You got to go 3 sig figs because I have 3 sigs. All right, that sounds fun. Wait, what's the units? You left off those. Nice job. Nice job. People never figure that out. Nice job. Yeah, is that all, Mr. Service?
Yeah.
Because first hour, not there. I had to give it to him. So your units work just, and this is the same thing we did with Stoic, your units are just like numbers, right? So you had atmospheres on top. So atmospheres are still on top. You had liters. And on the bottom you had moles. And you had Kelvin. So they don't cancel out. So they still are those. So that's your unit for this R. Which, coincidentally, why do I keep doing that? There we go. Coincidentally, if I change part of this, like let's say I didn't use atmospheres, what would that do to this number? Well, it wouldn't be wrong, it'd just be a different number, right? So this is R, but there are many R's. They're all the same R, but depending on your units you chose to use. This is the units I use a lot. But let's say you were a metric purist. You're like, oh, I love my metrics. Well, you wouldn't use atmospheres, you'd use pascals, right? And that's the one I actually always remember. I never use it, but I always remember it. And that R is like 8.314 kilopascals, liters, moles, Kelvin. You know how I remember it? I think this is the stupidest trick, but it cracks me up all the time. It's 8 pi. It makes me laugh like all the time. So I always remember that one. I'm like, oh, it's 8 pi. It's 3.14. Oh, that's silly. So this R has to have a name. The name we give to this R is the ideal gas constant. Or we could say ideal gas law. A lot of people say that. Ideal gas law constant. The problem is it's only for these gases that are like good. They behave. Like they have to follow your Boyles, your Charles, and your Gay-Lussac's. They have to follow that. If you're a gas that doesn't play nice, that doesn't follow those rules, this doesn't work. Again, it's that misconception people have that if you say the word law, then it means it's true. And that's not what a law means at all, right? Laws mean that it's cute and pretty. Make sense? What would make a gas not be this way? Can you think of that? Think about that for a second. We can actually rearrange this so it's not a fraction, which I like to do. So most of the time I'll write this like this so that it's not a fraction anymore. And notice how it's a formula. It is a law then, and this is going along with that. The ideal gas. So So it's called the ideal gas law because it's dealing with how a gas would behave if it was behaving ideal gas. It would follow that pattern due to Boyle's law, Charles' law, Gay-Lussac's law. So it's just another one of those kind of laws. And the R, I had to say this a lot last hour, so we'll preface it. The R is this, right? So a lot of times people will start working on like math with these formulas, and they'll go, how do I figure out my R? You don't ever figure out R. This is R. That's what makes it a constant, right? It never changes. It's like the speed of light or gravity. You don't figure those out. They is what they is. So the gas law constant is 0.0821, and that's what you would always put for this R value. Do you follow that? And that allows you to figure out everything else. You also see why the units are important, because it gives you the units for every other variable that you're trying to figure out. So you can figure them all out as you go. But let's go back to the question. What makes a gas ideal? Right? What makes it perfect? And you've got to think to yourself, what do you think of when you think of a gas? What properties does it have? Because that would be what makes the gas perfect, right? Otherwise, if you don't kind of get it written down, everybody has their own definition of perfect, right? I mean, like when you're talking about like humans, most people, I mean, this is what they envision, right? Not everybody though, and you got to take that into account. You got to give it a definition. So what's a perfect gas to you? How does it behave? Like when you think of a gas, what are things you think of? Are you all bashful? It's so cute. Think of a gas. If someone's like, hey, describe a gas to me. How would you describe it? What would you say?
When?
Huh?
When?
But gases aren't. That one won't work. Right? Carbon dioxide doesn't burn at all. Argon, we use it in welding because it won't burn. Xenon, none of those, they don't catch fire. So that's a good start, but yeah, not quite. Yeah.
Lots of energy.
Lots of energy? What do you mean?
Like fast moving.
They're fast moving. Would everybody agree to that? So gases are moving all the time. How do they move? How do gases move? Yeah.
Just randomly.
Yeah, and they're always doing it, right? Let's change move to motion. That seems to work. That sounds more sciencey. So random motion, and we said it's constant, right? So their particles are always moving around, right? The little kindergartners, they're always going. Constant random motion. What else about gases? What else do we know? Yeah. They fill up the space. Why? Okay, so they're constant random motion. They fill up their space because of that motion. What else is true about them? What about the size of their particles relative to, I don't know, pick something. The space they occupy. You said they occupy a whole space. So what is their size like compared to that space? Big, little, little. So they're tiny compared to the amount of space they take up. Right? That'd be, right, all the particles are packed together. So there's not a lot of space between them. So those don't have that. But a gas, they're like really, really far spread out because of that random motion. So how do we want to write that? Small relative to space. Maybe distance between. What else has to be true about them? When we talked about pressure, right? So that constant random motion means what's going to happen to those gases. And I'm thinking pressure now, sorry. So they're in constant random motion. What's going to happen that contributes to pressure? Talked about it a little bit. They're going to hit each other. What has to be true about them hitting each other?
They're attracted.
They're not attracted to each other. So what does that mean about when they hit? Well, they don't necessarily repel. They're not attracted or repelled. So what happens when they hit each other? They just bounce off of each other, right? They hit, they bounce. What is physics term again? What's it called when things like hit and they just bounce off perfectly every time? Do you remember the physics word for that? Some of you had physics, right? Yes, no? Oh, yeah, whoever said that. Elastic is what that, elastic means that things hit and they don't lose any energy. So they don't lose any of this motion energy. So in physics, you would call that an elastic collision. But Sophia hit on the really, really key point here. That's kind of big. So if this is what an ideal gas looks like, it has these properties, what would cause it to not be ideal? And she said, well, what if they attracted each other? Why would that screw these up? What would that do? Yeah.
It would stop the random motion and then the distance would become closer.
Right? Do you guys follow that? If they had attraction, right, they're not going to move randomly anymore. So think about some dude who's like really attracted to a girl. He doesn't randomly move through the halls anymore. What does he start doing? He tries to move towards her, right? He's a creeper. Starts stalking her, being right outside her second hour, waving outside the door. See, there's one right there. Danielle looks, who is it? I don't know who it was actually, but that was good timing. Right, so all of a sudden that random motion changes. All of a sudden the collisions aren't elastic, right? If they're attracted when they run into each other, they might run into each other. If they're not attracted when they run into each other, then they might push off even faster. So yeah, attraction would do that. So what would cause a gas to be attracted to each other? What force would cause them to be attracted? Uh-oh, we are definitely going to fail our test. Ooh, a London dispersion force would cause things to be attracted, right? What things have London dispersion forces? Oh, thank goodness, because that's the most missed question, right? What other forces could there be? Dipole. And finally, what gas, quickly, you should have one. There is a gas that has huge hydrogen bonds, right? So it would not fit these. It would not be an ideal gas. What gas can you think of right now that has hydrogen bonds? So much so you probably think of it as a liquid. It's good to have counterexamples for things. What do you got? Gas that has hydrogen bonds. All right, scratch that. Think of a molecule with hydrogen bonds. What molecule can you think of that would give hydrogen bonds to each other? Water. Hey, wait. Can you think of a gas that would have hydrogen bonds? Oh, water. Water vapor, right? There it is. Do you see it? Humans produce lots of it, right? We're always producing water vapor. Water vapor is not a very ideal gas because it has hydrogen bonds. It's super attracted to other water molecules, right? That's why it condenses on things so easily, right? Like if I went on a mirror, you would see the water vapor, except it wouldn't be water vapor now, it'd be liquid water on the surface because it's not really ideal. By the way, we could probably add, I don't know, 2 or 3 more to this, don't you think? If we tried? You'll notice it's not very pretty. What do we call it when things aren't pretty? You remember? They're theories. This is a theory. You can start seeing why it upsets chemists when people think theories are not true. Do you follow this logic? Well, it's just a theory. It's not real. No, this is a theory. It is 100% totally real. It's ugly, so we call it a theory. This is the ideal gas law. It is not true. It doesn't work for water. It doesn't work for gases on the sun. It doesn't work for a gas under tremendously high pressure because it screws up the small relative. It's still a law. It doesn't make any difference whether it's true or not. It's cute, it's pretty, and we can prove it with a specific situation. Just like Boyle's law. Do you follow that? That's why it's so irritating to science people when they're like, oh, that's just a theory. It doesn't, not real. Nobody proved it. That's where normally like a weird finger comes up and you're like, True story. This is called, by the way, and I think you can figure out why it's called this once I write it. We call this the kinetic, I might have spelled that wrong, molecular, theory. So this is called kinetic molecular theory. You can Google kinetic molecular theory. It'll pop up. It's in your textbook, I want to say, beginning of chapter 11, beginning of chapter 10. I think it's in both spots, both chapters. And it's just not a very pretty thing. It's not like a proving thing. But it says simple things that you know. That particles are always in motion. Yes, even the particles in the desk, right? You were taught that back when you were little. That gases specifically are in random motion. It says things like, hey, gases have elastic collisions. It says things that their temperature is their average kinetic energy, that their pressure is resulting of those collisions. It just describes all of those properties. So we don't call it a law, we call it a theory. In order to use this law, we use it a lot. It works best if they follow kinetic molecular theory. If they don't follow kinetic molecular theory, this law falls apart pretty rapidly. Do you follow that? For us, our normal day-to-day life, this law works pretty darn well. And it's important to us because let's pick something fun. Let's say you're an anesthesiologist, right? Some of you might want to do that. It's probably one of the highest paying in the medical field. It's a good time. You're pumping a gas into people, right? They put the mask over your face. Count backwards from 10, right? They're pumping you full of a gas. When that gas goes into you, what happens to these variables? They change. They're giving you a specific mole of gas to knock you unconscious. It's specific due to your weight. Anesthesiologists make the most money because they kill you. That's the reality. They screw up their formula, people die. They get paid a lot of money because of that. It's a lot of risk. Right? Everything has a trade-off. They have to get the moles exactly right to knock Sydney out to replace her knee. It would not even touch me. I require a lot more moles of a gas to knock me out. Does that make sense? Because I'm huge. So they have to know that. When they put it in our bodies, it's going from this temperature to my temperature, which is a lot higher. When my temperature goes up, what does it do to the volume of the gas that just went inside me? What's it do? Yeah, it goes up. Oh, weird. What's that do to the pressure inside of me? It goes up. If I screw up my calculation, not only could I give Sydney too much of the drug, bad, I could also do it at the wrong temperature conversions and pressure conversions from the tank to actually explode her lungs, which would also be bad, right? So knowing exactly how that gas is going to behave, kind of an important thing to us, right? Knowing what's going to happen to my car tire, because I set the amount of moles when I fill it with the gas, when the temperature changes from yesterday at 40 degrees in the morning to yesterday afternoon when it was 70, and we had that 30-degree jump, what's that going to do to the pressure and the volume of my car tire? Kind of important, right? Because if it changes incorrectly, then my tire loses all stability on the road, which could be dangerous to other people. Not so dangerous to me because I'm inside the car and there's lots of protections. People walking by on the sidewalk, not so much. Do you kind of follow how this ideal gas law just like ties into stuff? These are the variables we need. So that's where this kind of comes up. The problems for this aren't too bad once you get the hang of it. All right, so we're going to do a few of them here, like 6 or 7, to see how we